Okay, I think we'll get started. Today we're going to look at 3D force systems. We'll look at that a little later. We're actually going to start with just the idea of resultants. We kind of skipped over that last time with our 2D concurrent force systems, but we're going to look at a little bit. We're going to maybe back up even and talk about resultants. So let's start there and look at this. So resultants. So what I mean by resultants, I'm talking about a lot of times you'll have a system, well, almost every time you'll have a system with more than one force applied to it. Maybe it's a ball that's got gravity and somebody pushing on it, so it's got two forces on it. And it's rolling on the ground, so it's got a third force. And maybe there's friction, so there's a fourth force. So there's all these forces that are acting on our system, our body of interest in our free body diagram. And sometimes what we want to do is figure out a resultant. Now, last time we did 2D concurrent force systems in static equilibrium, and the key to that is that in static equilibrium, the resultant is zero. That's the point, is that there is no net movement. There's no net force that isn't imbalanced somewhere else. But in general, you could have a resultant that is not zero. So I'm going to define resultants. I'm going to define it as a single force, and I'm going to put in parentheses for now, and a torque. So remember, torques, moments, those are trying to rotate something. We're not looking at rotation just yet in this course, so that's why I put it in parentheses. So we're really just looking at resultant forces currently, but technically there needs to be a resultant torque also. So a single force that has the same effect as all the forces that were originally on the body. So that weight and that external push and the frictional force and the ground react, all those things combined together are combined into a single resultant, which is a single force that has the same effect as, let's just make it all original forces on the body. So we can do a really simple example like this. Let's say we've got a body, and our body's just going to be a circle. So really simple. We have a force applied to it, and that force is 10 pounds. And then there's another force. Somebody else is also pushing on the thing with 5 pounds. The resultant of this would be both of these are going in the same direction. So we'd have a single resultant force that's just 15 pounds. So that's a simple way to think of resultants. Another simple way, maybe I've got that 10-pound force I'm pushing with, and the other person over here, now they're pulling 5 pounds. So the resultant would be a net effect of 5 pounds. So 10 minus 5, because they're counteracting each other. More often than not, they're not all lined up on, they're not collinear like this. Maybe they're more often at some angle. So now I've got a body. Now this is not static equilibrium. Again, if this is static equilibrium, then basically the 10 pounds going to the right is balanced by a 10 pound going to the left, and the resultant is zero. So that's static equilibrium. This is not static equilibrium because both of these forces are pushing upwards or pulling upwards, and nothing's pulling downwards, so this little dot would be accelerating some direction upwards. Now there's a, well, let's put, well, let's not do that yet. There's a parallelogram. I don't know if you'll call it rule, but I'll put rule. Where graphically we can work with these things. So just kind of like I did here where I drew the 10 pounds and drew 5 about half of that, and the 15 is, you know, 10 plus 5, so it should be those two lengths added together, so it's longer. So if you're really careful with your drawings, then you can use graphical means to do some of this stuff. And so how you do that, if you have two forces, it doesn't matter if it's just two, but if you have multiple forces, you take one of them and move it. So take the tail of it and move it up to the head of the other one. So something like that. So this moved force is parallel to the original one. And if you had another force, you'd add it on to the tail of this one and then keep adding them all together. And the parallelogram rule would tell me that if I took a line from the original origin where these forces started, where that original force started, and drew from there to wherever the last one ended, you know, if I had a whole chain of these, wherever that last one ended, that would be the resultant. So this guy would be the resultant. And if you did really careful job of making this, you know, 10 pounds, and this, it looks like it's 60% of that, so maybe 6 pounds. And if we did a good job of putting our angles in here, so let's see, that one, I don't know, that looks like a maybe 40-degree angle. Let's do it in blue. And this one, that looks kind of like a 45-degree angle. So if you did a really good job of measuring and drawing things, then the length of this vector kind of gives you an indication of what you could expect if you were to calculate the resultant. So looking at this, it's longer than the 10. So maybe it's not much longer than the 10. So maybe this is 11, I'm going to put approximately 11 pounds. And that's at a really steep angle. So maybe that's like 75 degrees. So it gives me a way to approximate the resultant. But it also gives me a way to kind of check my answer, because if I really wanted to solve for this resultant, what I do is I do the same thing I did last time with summation of forces in the x direction equals, but last time I put that they equal 0 because it was in static equilibrium, everything balanced. But now the summation of forces in the x direction just equal the x component of the resultant. So this guy is x component. Same thing for y, except they equal the y component of the resultant. The magnitude of the resultant would just be the square root of the summation of the squares of those components. So that's just Pythagorean theorem at that point. A squared plus b squared equals c squared, just solved for c. The angle theta would just equal the inverse tangent of ry over rx. Oh, almost off the bottom of the screen. There we go. So if we wanted to put numbers into here, we could do that. We could write this equation, summation of forces in x equals the x component of the resultant equals the x component of the 10-pound force. So remember right here, all I'm doing is I'm remembering that cosine of theta is equal to the adjacent side over the hypotenuse. In a minute, we'll need sine of theta being the opposite side over the hypotenuse. So we're just remembering those from last time. So this is the x component of this 10 pounds. So it's the, if I were to project this 10 pounds down to the x-axis, it would be that long. The vector would be that long. This one's negative, so minus 6 pounds times the cosine 45 degrees. And those won't add to 0. They're going to add to the x component of the resultant. Let's see what the number is. 10 cosine 40 plus, or no, minus, whoops. 10 cosine 40 minus 6 cosine 45. I put an x in there. Eventually we'll get this right. 10 cosine 40 minus 6 cosine 45. 3.42 pounds. And so what that says is the x component of this resultant, right down here, would be 3.42 pounds. Then we can do summation of forces in the y direction, and that's going to give us the y value of the resultant's y component in the y direction. So 10 pounds times the sine of 40 degrees, and then we have 6 pounds. Also plus, because both of these forces are in my positive y direction. I didn't label these, but we're pretty much always going to assume y is vertical and x is horizontal. So we add these two together, and we get 10 pounds sine of 40 degrees plus 6 pounds sine of 45 degrees, and we get 10.67. All right, to get the value, the magnitude of the resultant, we do the square root of the summation of the squares of its components. It's a lot to say. R equals the square root of 3.42 pounds squared plus 10.67 pounds squared. All of that under the square root symbol. 3.42 squared plus 10.67, or 67 squared. We need the square root of that. 11.2 pounds. We had guessed it was 11 pounds just from our picture and our really rough, guessing. And so that confirms at least well enough to me that I drew this relatively accurately. I didn't measure things, but it's relatively accurately, and I predicted 11 pounds. I got 11.2. I'm actually surprised it's that close, but if it had been anywhere from 9 to 12 or 13 pounds, I would have still felt good about, well, yeah, that's probably right. And then theta is inverse tangent of ry, which is 10.67 pounds, over rx, 3.42 pounds. So remember, tangent is the opposite side over the adjacent side. So if I'm looking at this angle, the opposite side is the y component, the adjacent side is the x component. That's what I'm doing here. So we have 10.67 divided by 3.42, and we want the inverse tangent of that number. 72.2 degrees, equals 72.2 degrees. We had thought maybe it was a 75 degree because it's pretty steep. So again, that tells me that, since I took a little bit of time and drew this relatively accurately, and I guessed numbers that, based on this picture, and I got numbers based on my calculations that are similar. They're not exactly the same, but they're similar. They're not out of scale. This isn't 700 degrees or something like that. I can be kind of certain that I've done the math correctly. I didn't make a mistake. I didn't leave off a negative sign. I didn't leave this negative sign unaccounted for or something like that. Because that's an easy mistake to make, is to put an addition there, or maybe flip a sine and cosine somewhere. And if you do that, chances are you aren't that close when you go to calculate these to what you originally thought. And then you have to wonder, did I draw this wrong, or did I make a mistake in these calculations somewhere? So it gives you a little bit of a check on your work. So that's resultants. They're not necessarily going to be static equilibrium. They do have a value. Not going to add to zero. For the rest of what we're going to do today, we are going to go back into static equilibrium, but we're going to go into 3D. So I'm going to get this out of the way, and I'm going to put it somewhere, find a spot for it. We're going to use some special paper, if I can find it. that I have printed out. So isometric dot paper. This is stuff I printed from a website where they have free isometric paper generators. I'll put the link to that website in the description once we're finished doing the stream. But you can create your own types of grid papers, not just isometric. It has all kinds. I think it has music paper, grid paper, rectangular paper, all kinds of papers. Logarithmic probably in there. I'm not sure if that's in there actually, but I'll link to the site so you can make your own if you want to. But what this paper is good for is that the dots are arranged in a particular way, and if you look at it, you can see there are lines of dots that are lined up at one angle. There are lines of dots that are lined up at another angle, and then there are lines of dots that are lined up vertically. Sometimes you see this paper and it's the grid, so instead of dots, it's a bunch of lines everywhere. To me, that's a little bit difficult because it's so, busy with lines everywhere. But the point of this is it's isometric. So iso is equal, metric is measure. So it is a way to create three-dimensional drawings that don't have any perspective built into them. So perspective is when things taper off into the background because it's it's the depth of them. So the way we see in perspective, assuming you have two eyes to converge on the objects you're looking at, then you can see in perspective. But isometric removes the perspective, so everything's in equal measurement. So how it would work if you were trying to draw a block of some kind. So you could use, and we're not being specific, you can set your grid to whatever unit system you want. Each little space between a grid dot could be 1 inch or 1,000 yards, it doesn't matter. But the thing is that it's the same distance from any two dots that are adjacent. So that's the same distance. So it keeps things equally measured in all these directions. So we could make a little, I don't know, whatever we wanted to make. And it helps us with creating three-dimensional objects. Now we're not going to use it for three-dimensional objects, we're going to use it for three-dimensional forces. But you can make any particular shape. I like, if I'm drawing three-dimensional objects for some reason other than maybe a free body diagram or whatever, or whenever I'm using this, it's kind of nice to give them a little bit of just shading so that you can kind of pick up the dimension, because some people look at it and they actually see the inverse of what you're trying to draw, where other people look at it and see actually what you are drawing. So it kind of helps when you just give some flat shade so that people can get the correct vision for what you're drawing. Now, when we're doing forces, obviously we can't shade in a force, but something like that. So we got this little kind of piano-looking block. So that's how isometric paper works for drawing objects. Now, for drawing forces, we need a coordinate system. So I'm going to go down here, and we'll have an x-axis. We'll have a y-axis, and now that we're in 3 dimensions, we're going to have a z-axis also. And if we're in a concurrent force system, then pretty much the origin of this coordinate system is the origin of our concurrent force system. So it's where all the forces will, at least their lines of actions will intersect there. Whether or not the forces themselves are applied there, that might be different. But what I would do is draw a force that begins at this origin, and then it will go out into this 3-dimensional volume of space somewhere. So maybe it goes out here. Now, that by itself is still ambiguous. Some people look at that and it looks to them like, well, it's just laying down flat in the XY plane. Other people, maybe it's slightly below the XY plane. Other people, maybe it looks like it's coming kind of straight towards their left side, or whatever. So in order to clarify where this actually is, the way I'm going to do it anyway is like this. I'm going to start at the point or at the origin, one or the other, depends on what I'm doing with it, but I will kind of indicate that, okay, you have to drop down to this point to get down to the XY plane. And then you have to go back that far to get to the x-axis. And then you have to go over this far to get to the origin. And so I can use those three distances to give this endpoint a coordinate set of x is -2, y is negative, remember my positive x is this way, positive y is backwards, towards the, pointing backwards. So negative 1, 2, 3, 4, 5, 6, 7, 8 for the y direction, and positive, I'm in the positive z direction, 1, 2, 3, 4, 5, 6. So I could give that endpoint for the force vector a set of coordinate x, y, and z coordinates. I suppose I could go and just label all of the distances on these lines, and then you could figure out the coordinates based on the labels. And we'll do both ways. One of the things we'll need to do with this is we need to calculate the length of this force vector. So this force vector represents some kind of, maybe a cable is pulling on something, or a chain or whatever. It could be that it's pushing on something. I drew it as pulling, but this arrow could be pushing on the origin here. So there's some kind of force there, but right now what I'm interested in is the actual length of this line. And to get that, it's simple. It's the same exact thing we just did for the length of the resultant vector, except now we have three components for it. So the length of this line, if we called it L1, I guess, we'll have to write that over here. Actually, let's slide them the other way. Do that. L1 is just the square root of x, y, and z. So -2, let's put inches. I didn't actually define my unit system, but let's just say it's inches. -2 squared plus -8 squared plus 6 squared. And we could actually calculate a length there if we wanted to. Now, I put negative signs in here, but they do end up being squared. So in my calculator, I'm just going to put 2 instead of -2. So 2 squared plus 8 squared plus 6 squared. And the square root is 10.2. So a little check you can do here. It's tough to estimate distances on the 3D picture, but one thing you can do, anytime you do this process of taking all the components, squaring them, and taking the square root, the hypotenuse, or the resultant, is always going to be longer than any individual component. So my largest component is 8, or -8, but the absolute value of it is 8. So I know that the resultant is going to be at least larger than 8. And I'm at 10.2, so I know that I'm probably calculating this correctly. It is possible that it could be way larger or not much larger, and so that's harder to tell. It's hard to estimate. Is it supposed to be like if I calculated 100 inches here, and these were the numbers I was dealing with, I'd have to at least question, like, I don't think you can get 100 out of 2, 8, and 6. So at every little step that you can, you should make a little, is this reasonable, check in your mind. And yes, 10.2 is reasonable to be the length of a vector defined by those components. So I'm okay with 10.2. There's another thing. So in our previous 2D world, we would have a force, and we just call it F, and just for completeness we'll put X and Y, and we would have an angle theta, and we would say that the cosine of theta is equal to the x component of this guy over the hypotenuse. So we'd say that. If we were to write this out, I'm going to put theta x in here because we're going to have to be a little more specific in 3 dimensions because we have a lot of these angles. So I'm going to be more specific on my 2D first, and then we'll move over to 3D. So I'm going to say theta x, and I'm going to say that theta x, and I'm just going to describe it here. So theta x is equal to the angle between the force, in this case F, and the x-axis. And I'm going to make another angle just over here. I'm going to call that one theta y. And I'm going to say that theta y is equal to, and I'm going to describe it, the angle between the force F again, and in this case I drew it between the y-axis and that angle. And we're going to use this same idea of an angle between a force and an axis over in 3 dimensions over here. So when I do that, I'm going to have theta x over here would be the same definition, the angle between the force, the red line, and the x-axis. Now it's going to be hard for me to draw, but you know, something like that. Theta x. And theta x is going to equal the same thing it equaled in 2 dimensions, where it is the x component of this force divided by the hypotenuse, the length of the red line, what I have labeled as L1. So theta x is going to equal, or well, the cosine of theta x equals that. I don't know if I specifically said cosine a minute ago. Theta x, cosine of theta x equals the x component of the force over the hypotenuse, which is the length of the force or the magnitude of the force. Okay. I will also, so one important difference, or not important difference, but one thing that is confusing for some people is over here, this theta x and theta y, they're both in the xy plane because it's all 2D. It's just in one single plane. Theta x over here is in a new plane that is created by the x-axis and the red line, the force. So it's at an angle, you know, it's at a plane that's a new plane. It's not the xy plane, it's not the xz plane, it's not the yz plane, it's in its own plane. That's why I kind of drew it flattened out, trying to show it in that plane. But I need 3 of these angle measurements to fully define where this force exists in space. So I also need a theta y, where the cosine of theta y is going to equal the y component of this force over its magnitude, and it's going to be, you know, somewhere over here. And then I need a theta z. It's going to be over here. And theta z, just so we have it written out, I think you see the pattern, but just in case, there's theta z. Is the z component, the cosine of theta z is the z component of the force divided by the force, just like it is in 2D, only now these are each, theta x, theta y, and theta z are each in their own plane created by whatever axis they're measuring to and the force. So those are 3 different planes, all, you know, spread out. So it'll take 3 of these angles to define where this force vector exists in 3-dimensional space. We only really defined 1 angle here. We've defined 2. By defining, when it's in 2D, we usually wrote down 1 angle, but by default we had implied the other angle. We just hardly ever wrote it down. So it did take the two angles to define it when it was in 2D, only we never really had to write the second one. But in 3D, we need all three of these. And we're going to do the same thing that we did last time, where if this is, now this is not in static equilibrium because there's only one force. So unless the force itself is 0, then this thing is not in equilibrium because there's nothing to balance it. So we need to create us a system that does have multiple forces on it, and put it in a system, coordinate system, and apply our same equilibrium equations to that system. So let me get a new sheet because it's not going to fit on here. And we'll just kind of go in the middle here and create us a new system. Now, this one, let's just draw our coordinate system first. I'll be more careful and use my ruler this time. So there's our x-axis. We'll put our y-axis. You might think it's odd that I'm drawing the y-axis in what you might think of as the negative direction, because maybe you normally think x should or y should go this way. You can draw x and y whichever direction you want to, but there's a convention of once you define x and y, the location of x and y relative to one another will tell you where the z-axis is. And I want my z-axis to point upwards, and by that convention, the right-hand rule is what that convention is called. I need x and y to go in these orientations so that my z-axis goes upwards, and because I don't want my z-axis going downwards just because I don't want it that way. So this is the x, y, and z layout for if you want the z-axis going upwards by convention. All right, we need to put some forces on here. So let me get my red marker. Let's see, it's probably going to be, in this case, simpler for me to draw the little lines that show where the force goes and then draw the force itself. Otherwise, I might end up with the force in the wrong spot. So I'm going to draw the lines first and then the force. So the coordinates for force 1, cable. So what we're thinking of here is, let's go back to our 2D equilibrium problem with, we had the I bolt and it was bolted to the ground. So let's think of something similar to that, where I've got some kind of I bolt, and in this case I actually know what force is pulling this thing down. So maybe this I bolt is connected to a crate or whatever, and I'm trying to lift it up with 3 cables. Whatever it is, I know that this I bolt is being pulled downwards with 100 pounds of force. And you have to know something. You have to know one of the values of the force. Otherwise, you can write all the equations, but if they're all unknown, you can't actually solve for them. So you have to know one thing. And so I'm going to say that this is the thing I know. So I've got my little eye bolt there. Something is pulling downwards on it with 100 pounds, and I've got 3 cables pulling in various directions upwards. And so cable 1 for the x-coordinate has a -8 inches for the x-coordinate. So positive x is this way, so negative x must be the opposite of that. So 1, 2, 3, 4, 5, 6, 7, 8. There's -8. In the y direction, which is this way, it has a +6. So 1, 2, 3, 4, 5, 6. And then it has a +6 in the z direction. 1, 2, 3, 4, 5, 6. So if I were to draw the vector for it, the force in the rope, it would start at the origin, it's connected to our little eye bolt, and go out that way. Kind of missed. There we go. We'll call that F1. We don't know its actual magnitude, we just know it's that direction. Oh, and we'll put the coordinates on it. So this was 8. It's actually -8 because it's going in my negative x direction. this was 6 in the y, in the positive y, and 6 in the positive z. All right. Cable 2 has a positive 3 x component. It goes up 3 in the positive x direction. It has a positive 7 in the y direction. And I made them all positive 6 in the z direction, so it also goes up 6. So that's where it ends up at. And its vector would, do something like that. And we would just call it F2. And it would have 3, I think this was 7, 7, and 6. These are all going to be in inches. I'm just trying to, normally I really don't like not putting units on things, but these 3D things get really cluttery as they are, trying to show all of the dimensions and forces and everything. So I'm leaving off the inches just because they're really cluttery as it is. The third cable, so this is 2 cables kind of pulling backwards. The third cable is going to come out this way towards you, and it's going to have a 0 x component, so it's going to be on the y-axis here, and it has a -5 for y, so 1, 2, 3, 4, 5, so -5 for y, and a positive 6 for z. 1, 2, 3, 4, 5, 6. So I should have thought about those overlapping, but I didn't, I guess. And it's going to come out and do something like that. And we'll call it F3. All right. Now I'm not going to draw all the cosine symbols on here because each one of these forces, including the 100-pound one, has 3 cosines. Each one has a relation to the x-axis. Each one of the forces has a relation to the y-axis, and each one has its own relation to the z-axis. So there would be 9 little symbols in there, and they just get too crowded to make sense of any of it. So what I'm going to do now is we're going to end up with a system of 3 equations. We have the summation of forces in the x direction equals 0, the summation of forces in the y direction equals 0, and the summation of forces in the z direction equals 0. So we have 3 equations. We have 3 unknowns, F1, F2, and F3. So that's good if we have 3 unknowns and 3 independent equations that are related to those unknowns. And we're going to have to solve this simultaneously. So I am going to solve this. I'm going to do it kind of generically, but I am going to do it in MathCAD. And let's go to MathCAD now, and then we will probably flip back and forth to the other screen as we need to. But let's go to MathCAD right now. So here we are in MathCAD. And the first thing that I am going to do is I'm going to take, maybe we can get this kind of on the screen, kind of over there on the side. I'm going to take and define the x, y, and z coordinates of the endpoints of F1, F2, and F3. So what I mean is I'm going to say that x1, so the x component of the x component of force 1 is equal to -8. So you can kind of see it on there. I had to make sure that I was actually the 8 and not the 6. It's the -8. It's -8. I will use units just because I can use them over in MathCAD and it's not too cluttery. Y1 will equal 6 inches. You can kind of see that one there. And Z1 is also 6 inches. And then we'll do the same thing for force 2. And we're just defining the x, y, and z component or coordinates for this point up here. So x2 is 3 inches, y2 is 7 inches, and z2 is also 6 inches. And then see if we can get force 3 on there. Force 3, x1. Now, even though it's 0, I still need to have it as part of my equations, and we'll set those up in a second, and I'll show you why. So y3, oh, I put x1. x3 is 0. y3 is -5 inches, and z3 is 6 inches. All right, so we have defined all of our components, or well, the coordinates of our 3 different forces. One of the things that we need to do is remember all of these cosines have I wrote as F, but it's the hypotenuse for all the forces. So I'm going to calculate the hypotenuse, but I'm not going to calculate it as a force. I'm going to use actual distances. These x, y, and z numbers that I have here are distances. So I'm basically going to calculate the length of cable 1, and the length of cable 2, and the length of cable 3. And they're really just force vectors, so their lengths don't necessarily relate to their magnitudes in this case. It's really just so I can get their actual directions. So length of cable 1 is the square root of x1 squared plus y1 squared plus z1 squared. And I wanted it in inches. There's my little number again, 11.7 inches. I look at all the numbers associated with cable 1, and they're 8 and 6. So 11.7 seems reasonable to me. It's larger than all of those, and it's not totally out of scale with those numbers. L2 is going to be the same thing, except I'm going to have all 2's, x2, y2, and so forth. Same thing, my largest number there's a 7, I have a 9.7, those seem reasonable to me. And then we just need to do the third force. And it also looks reasonable with these numbers. Okay, now what we need to do is we need to go in, and you normally probably wouldn't do this next step as thoroughly as we're going to, but it will probably help us make sense of what's going on. So we're going to go back over to our paper, and we're going to write out our summation of forces in the x, y, and z equation. So summation of forces in the x direction equals 0. So what this equation says is that we need to take every force component in the x direction for our system, and they need to add to 0. So the 100 pounds, it doesn't have an x component. Actually, F3 does not have an x component. So it's only F1 and F2, but I can't actually ignore these two because they are part of my system. And I can't ignore them because of the way that I am going to set up this solution to these simultaneous equations. So what I'm going to do is I'm going to say that summation of forces in the x direction equals 0 equals F1 times the cosine. Now, you might look at F1 and it has a negative, it's going in the negative x direction. I am going to, in this case, let the cosines themselves take care of the negative signs because it's just too complicated if I don't let the cosine value itself take care of the negative sign for me. So I'm going to write these all as plus, all positive. So F1 times cosine of theta x1. So what this is this is the angle between the x-axis and force 1. So that's the x and the 1. And then I'm taking the cosine of that. And that cosine, when I take the cosine of that number, it will be a negative number itself because F1 has a negative x component. Remember, we wrote this. So let's evaluate this 1 just so we have it. Cosine of theta x1 would equal the x component of the force 1. I don't know the x component of the force, but I know the x component of the cable. and the x component of the cable is -8. And then the bottom, the denominator here, is the hypotenuse. I don't know the magnitude of the force, but I know the length of the cable, which is L1, which on my, I'm looking at my MathCAD, it's 11.66. So I actually have numbers that I can put in to this expression, and it can just be a coefficient at that point. I'm going to write them all as the expression, and we'll let MathCAD deal with the numbers in a minute. So let's finish writing our generic form of our equation. So all the x components, we would have f1 times its coefficient plus f2 times its coefficient, which is going to be cosine of theta x2, so the angle between the x-axis and force 2, plus, I got something in the way on my screen here from MathCAD. All right, f3 times cosine theta x3. I'm going to say it equals 0, and there is the possibility, in this case it doesn't exist, but there is the possibility that there is a, I'm going to call it Rx. So this force, 100 pounds, could have an X component. You know, it could be angled. In our case, this is going to end up being 0, but I'm going to put it here so that we have it because we're writing this very generically. So now I'm writing the y equation, and it looks very similar. In fact, you probably have to look really closely to see the difference. So the difference is I still have F1, still have F2, F3. I have a difference over here because the 100-pound load, the 100-pound load could have a different y component. Ours has 0. But it could have some number there. And then the angle is now the angle between the y-axis and force 1 or force 2 and force 3. When you're creating these systems of equations that you want to solve simultaneously, you have to be particular about the way you do things. And I'll show you the particulars once I finish writing this equation. All right, so there's our 3 equilibrium equations accounting for 3 forces and the other stuff. So the other stuff here I've just labeled as R. This R is the 100-pound force in its X, Y, and Z components. So this RZ is actually 100 pounds, or it's actually negative 100 pounds because it's going in the negative Z direction. Okay. What I'm going to create here is 2 matrices. So here's one matrix, a 3 by 3, and here's one matrix that has 3 rows and only 1 column. And I'm basically just trying to write out these equations in a matrix form. What I'm going to put in the 3 by 3 matrix is the coefficient that goes with each one of these variables. So the variables are F1, F2, and F3. They could be any 3 variables that you have. In my case, the 3 unknowns are F1, F2, and F3, so they could be whatever you needed. You do have to line them up in all the F1s, all the variable 1s have to be in the first column. Or they have to be in a column. It doesn't have to be the first column. It normally makes sense that if you have subscripts of 1, 2, and 3, that the 1s are in the first column and the 2s are in the second column, 3s in the third column. That's not necessary. It just kind of makes sense. What is necessary is that all of the 1s are in a column together. All of the 2s are in a column together. All of the 3s are in a column together. And then the rows make up the individual equations. So in this case, the equations are equilibrium equations, And so all of the equilibrium equation components related to x are in a row. All of the y's are in a row. And all the z's are in a row. And then when I go to create my matrix here, I'm going to call this my coefficient matrix. And it's going to be a 3 by 3 matrix that has only the coefficients of my variables in it. So here I would have cosine of theta x1, cosine of theta x2, cosine of theta x3. So I'd have all these cosines, right? I think I put a z there, it should be a y. So that's my coefficient matrix. And then I've got to create this matrix, which is going to be my residuals. That's why I gave it a R. And these are numbers in the equations that are not associated with a variable. So it's constant numbers. Sometimes you might have to lump several things together to get this number. In our case, the things that aren't associated with a variable are only the 100-pound force. But if I had two forces, if I had a 100-pound force and a 50-pound force, I'd have to lump those together to create this residual matrix. But in my case, I just have Rx, the x component of the residual, and Ry and Rz. These systems of equations aren't specific to 3D concurrent force systems. I'm trying to make it generic to systems of 3 equations. And you will always have coefficients, you always have residuals. They may be forces, they may be voltages, I don't know. But I'm trying to make it in a generic way. So how I solve for this is we go back to our original equation. We had F equals the individual forces components, so all these coefficients, times, plus the residuals. So F, how I solve this with matrices, I would take my coefficient matrix, take the inverse of it, multiply times my residuals. And I would get out a third matrix that would be, in this case, F1, F2, and F3. So the values of the forces in each one of those cables. So what actually comes out here is whatever you had in this first column. And what comes out in the middle is whatever you had in the middle column. And whatever comes out last in this matrix is whatever you had in the last column. So I did put them in order of 1, 2, 3, which made it 1, 2, 3 here, but what it is whatever's in the first column. All right, let's take this idea and let's build this matrix and this matrix in MathCAD and solve for that matrix. All right, here's MathCAD. We do need to remember that our cosines, all of our coefficients in our coefficient matrix, they were all cosines. But remember, we can evaluate every one of those cosines of some angle as the component over the hypotenuse, so the x component over the hypotenuse. So every one of these coefficients is a number. And we have all these numbers in MathCAD anyway. They're right here. So we have all the x, y's, and z's, and we have all the hypotenuse numbers here. So here's my coefficient matrix. It's going to be a 3 by 3. And in this first position, I'm going to have the cosine of theta x1, which is defined to be x1 over L1. So that number is the cosine of theta x1. Now we've got x2 over L2, and we've got x3 over L3. Here, this middle row is representing, and the way we set it up, it's representing the y equations. So I'm going to have y1 over L1, y2 over L2, and y3 over L3. So those are the coefficients that go with calculating the y component of force 1, the y component of force 2, and the y component of force 3. And then we do the z's. Now in MathCAD, one little thing does get lost right here that I need to point out, and that is that x3, this term right here, is actually 0 because the x component of force 3 is 0, but you do have to include it. Just because it's 0, you can't leave it out. It has a position in the matrix that needs to be accounted for, and so you have to put in zeros. So if you're doing this by hand or in your calculator, you can't just leave those out. You have to put zeros in there. In MathCAD, it's, it doesn't look like I put a 0 in there because I actually put x3, but x3 equals 0. My residual is also a matrix, but it only has one column. And here, I don't have anything for Rx, Ry, and Rz's. I'm going to put the actual numerical values. So there is 0 pounds for the X component of the 100-pound force pulling straight down. There are 0 pounds for the Y component, and there are 100 pounds for the Z component. And these are all pounds. Whoa, wow, that did not do what I wanted to do. There we go. Now, you might be wondering why I put 100 pounds in here and not negative 100. So remember, here's the equation. The RZ is the 100 number. So this equation is basically writing the summation of forces in the Z direction equals 0. So that equation is F1 Z component plus F2 Z component plus F3 Z component plus the Z component of the force, 100-pound force, equals 0. But to make this into a separate thing, I need to move it to the other side of the equal sign. So technically, this whole thing moves over to the 0 spot over here. And these were just already 0, so negative 0 doesn't mean anything for this. So these stayed 0, but this one, when it moved over, became a positive 100 because it's negative 100 over here. So you have to keep track of that part. Now all we need is to do our math. Coefficient, we want the inverse of that guy times the residuals, and just hit equals. It came out in pounds. I wanted newtons. I wanted in pounds. And these numbers, 22.6, that's the tension in cable 1. 50.1 is the tension in cable 2. And 74.7 is the tension in cable 3. And these are in that order because of the order I put them in here. You can kind of see all the ones, x1, y1, z1, are lined up here, x2, y2, z2, x3, 3, 3. So all the forces, or the variables, F1, F2, and F3, are lined up in such a way that the residual, or the answers, come out as F1, F2, and F3. These seem reasonable. I had 100 pounds applied to this thing, and it's spread out over 3 cables. They are not all equally spaced, so I don't expect them to share the load equally. So these numbers seem reasonable. That's the best you can say. If you had gotten one of these in the thousands or whatever, then you'd have to wonder how that happened. But these numbers seem reasonable. It does show that cable 3 is carrying more of the load than any of the others, and cable 1's not doing as much as the other 2. So that kind of gives you some ideas there. Okay. There we go. This is how one way to solve matrices. If you have, depending on what calculator you have, I have this one. It has a built-in equation solver over here, and you want to solve simultaneous equations with 3 variables, and it even asks for it. It looks like a matrices, so it's very similar to just doing the same thing, putting the coefficients in, putting the residuals in. And most calculators, most scientific calculators, are going to have a similar system for solving sets of equations simultaneously. Pretty much any scientific calculator can do this with the matrices, just doing the matrix math. You just need to know how to put the matrix into your calculator. So I'm not going to go through the different ways because there's so many different calculators and they all have their own little process. But they generally look something like this, where you're able to put in the equations into their solver. The important things are to remember when setting up simultaneous equations are that you isolate the constants by themselves. You put all of the whatever you're using them, F1, A, X, whatever your variables are, you put all of the same type variable in a column, all of the other type variables in another column, and if you had a third type of variables, they go into their own column. So you have to keep the variables in their own columns. Even if there's a zero coefficient, you have to have a spot for it and just say the coefficient is 0. All right. Based on some things from questions I had gotten earlier, I'm going to do one more thing, not really related to 3D concurrent force systems at all, but related to free body diagrams, and then we'll call it a day. And so this particular thing has to do with how do you draw a free body diagram when the thing is round. So specifically, if you have a round barrel and it's sitting on an inclined plane, so how do you draw this free body diagram? In this particular problem that they were asking about, there's also a cable holding this barrel up. The cable, I don't think is the problem. I assume most people can figure out if there's some kind of rope holding this thing up, whatever angle that rope is at, that's the reaction. We are in this series of course lectures, we're going to assume that cables can only carry tension. We haven't talked a lot about tension and compression. We'll get to that on Monday. But in general, tension means you're pulling on something. Compression means you're pushing on something. And we draw tensile arrows as pointing away from the free body. So the free body in this case is this circle. It represents kind of barrel that's laying on a rack somewhere. And this cable is pulling on it, so it's in tension. And so I think everybody's okay with that part, but how do you deal with this? So here's what you do. So if there's the plane, and it's at some angle. So let's make it a 70-degree angle, just to have a number in there. First, you have to know, is there friction involved in this or not? So for this particular course, almost always there is no friction involved. We wait till there's a more advanced course to deal with friction. If there is friction, then you do have a force down here, and it's no longer a concurrent force system. So let's assume that for whatever reason, the contact between this barrel and this plane is frictionless. So there's no friction there. What you do is you recognize that the reaction force between this barrel and this plane is perpendicular to the plane, or maybe better said, perpendicular to a tangent line at this point of contact, which is also the plane. So they're lined up. So we could draw that kind of like this. It is pushing on the barrel. You know, the plane here is holding the barrel up, so it's pushing on it. So that would be kind of a compressive force. If it gets large enough, you know, the bottom of this barrel flattens out there, if it's soft enough. But what angle do I put that at? So the easiest way to make things perpendicular that I know is the plane is 70 degrees from horizontal. So the perpendicular line to that, which I want the force to be perpendicular to this plane, the plane is 70 degrees from horizontal. The force is 70 degrees from vertical. And so that makes the force perpendicular to the plane. And you can kind of start to see it if you finish out the triangle. I missed drawing things accurately, but let's draw it there. And I end up with similar triangles right there. That triangle is similar to that triangle. The other thing I would do on a particular problem like this is remember that I could extend this line of action indefinitely if I wanted to. So I could extend it, and I could extend it in this way if I wanted to also. But I would rather extend it this way and take this force and apply it right here when I draw the picture, just to deal with my concurrent force system better. The barrel has some weight also that I would apply at that center of gravity. And that's what I would use for a free body diagram to deal with this type of setup. So I just wanted to go over that because I'd gotten a few questions about how to deal with free body diagrams and round things. So that's how I would deal with it, assuming there's no friction between the round thing and the flat thing that it's rolling on. Okay, we'll be back Monday, and we will talk about some mechanics. So all of this has been statics. We'll actually talk about mechanics. Remember, that's how are the materials themselves going to respond to all these forces. Are they going to break? They're going to stretch, twist, bend. We'll start out with everything just in axial forces. So that means they're going to stretch or compress. They're not going to twist or bend yet. So I'll see you all on Monday. Have a good weekend, and we'll be back soon on Monday.